Welcome to Induction Logic's January 7th, 2024 video. If you want to know the camshaft and cylinder head requirements for your engine combination and desired performance, Induction Logic engine modeling software can do that for you. But unlike all others, this engine modeling software can and will show you the reasons why its calculated results are true. Follow along as we model a 434 cubic inch small block Chevy, and you will witness the software's simplicity while it teaches you something about the engine you never knew or considered. Let's model that 750 horsepower, pump gas, street strip, small block Chevy. To make that much power, we're going to need cubic inches. So, we'll start with a 4.155 inch bore, a 4-inch stroke, and 6-inch rod. We'll enter 9 inches for the deck height, which gives us a 1-inch compression height. Select dome for piston type and enter 4 cc for dome volume. Input 39 thousandths for gasket thickness with a 4.2 inch gasket bore. We'll enter 1.85 rocker ratios to keep the cam lobe heights down and select 20 thousandths for hot valve lash and input 20 thousandths for valve deflection. Now, we have to decide on cylinder heads and the maximum horsepower RPM. We can start with the AFR 245, which we have all the information saved in the software. It has a 2-inch 125-inch intake valve, a 1-inch 600 exhaust valve with 8mm stems. The intake port volumes are 245 cubic centimeters, and the intake port flows 305 CFM at 500 thousandths of an inch valve lift and 345 CFM at 800 thousandths of an inch valve lift and above. Now we are going to raise the peak horsepower RPM to 7,400, where the peak piston CFM demand approaches the intake port's capability. At 7,400, the peak piston CFM demand is 340, which you might think is good to go, since the max port flow is 345. But we don't use the max port flow. If you'll notice, the 340 CFM is at 719 thousandths net valve lift. This is the net valve lift at the degree of maximum piston velocity of the cam requirement that is currently displayed on the screen. But this is the unadjusted camshaft requirement. So we will stop here and come back to this. At this RPM, our intake valve diameter and valve area is less than the calculated required valve diameter and area. This is common in race engines and will affect the performance if the camshaft is not adjusted. Now, pay attention to the intake cam 50 thousandths duration and net valve lift. As I lower the RPM to 6,100, the intake cam changed to 239.5 degrees duration with 634 thousandths net valve lift, and the required intake valve diameter is 1.999. When I raised the RPM to 6,500, the duration increased to 249, with 674 thousandths lift, and the required intake valve diameter is 2.062. At 6,900, it increased the duration to 258, with 714 thousandths lift, and the required intake valve diameter is now 2.123 inches, and still less than our actual valve size. So, increasing the RPM by 400 increased the valve lift exactly 40 thousandths in each case, and the duration saw an increase of 9 degrees. The required intake valve diameter has also been increasing with the RPM, and at 6,900 has reached our actual intake valve diameter. So when we increase the RPM another 400, what is going to happen when our actual valve diameter no longer meets the intake valve diameter requirement? To find the answer to that question, look right here at the mean cam design velocity and the mean intake valve curtain velocity. Right now, the curtain velocity is about the same as the mean cam design velocity, which is actually the same as the mean port velocity. So when we raise the max horsepower another 400 RPM to 7,300, the curtain velocity exceeds the port velocity and becomes a restriction. And the additional 9 degrees duration and 40 thousandths valve lift will no longer fill the cylinder. But don't panic, the software will automatically take care of everything when you select Auto or Auto Calc mode. Now your velocities are corrected, but to achieve that, we had to increase the valve lift by 80 thousandths of an inch instead of the 40 thousandths. The farther you exceed your valve area, the more lift will be added to compensate. So, you have now learned why at higher RPMs, the engine requires an unproportional amount of additional valve lift. It is to compensate for the intake valve diameter not meeting the minimum required valve diameter. Now, back to 7,400 RPM and the peak piston CFM demand. The port can now supply the demand, as raising the valve lift puts our 340 CFM at 768 thousandths valve lift. Let's take a look at what we have been talking about on our graph form. To save time, we have already designed and loaded the cam profiles. You can graph the cam lift, cam velocity, cam acceleration, and net valve lift. Net valve lift is graphed in red, the piston CFM demand is graphed in gray, and the intake port CFM supply is graphed in orange. Before I forget, we need to check out the performance form. Let's check the dynamic compression. That should satisfy 93 octane. 785 corrected brake horsepower. Quite optimistic. To learn more about induction logic, watch all of our videos on our YouTube channel at rickjones5908, or better yet, purchase a copy from our website at induction-logic.com. Thank you for watching.